Okay, this is lecture 3 for Biosci 101, spring 2021, digital images by me, Dr. Giorgi. So let's look at this. You might say, what is this? What does this have to do with microscopy? Well, let me give you some more info. This is a digital image. A digital image is a series of numbers in a grid. That is how you are seeing this image on your computer or your phone. And that is how nowadays we capture microscopy images, of course. So remember this as we go forward, and we'll come back to it. Okay, so what you've seen so far is that a digital image is a grid of numbers. Let's build up to understanding that. First of all, we're going to think about gray levels. Gray levels, so pretend there's no color for the moment so that we can understand digital images. We'll come back to color later. But think about, let's pretend that there's only two possibilities for each of these squares. One square can be black and the other square can be white. That would be considered two gray levels. Basically, black is super gray, right? It's the most gray of grays. There's so much pigment that it's actually really true black. And white is a lack of pigment. Let's just say in terms of printing. In terms of microscopy, it has to do with the amount of light and of photons that hit the camera. But let's start with just two possibilities, black and white. We would call that two gray levels. There's just simply a choice between two things. We can still make an image with that, but in most cases, it's a lot better if you have a little bit more variety. For instance, here's an example of 6 gray levels. Of course, each of them is outlined with black, but as you can see, there's a gradual distribution of levels in between purest black and extreme white. So here's an example with even more gray levels. And as you can imagine, the more gray levels, the better it is generally. It's a thing, just like in nature, nature loves variety and diversity. Generally speaking, for photography, for digital images, for microscopy, the more gray levels, the better for your printer, for your camera monitor, etc. It just makes the range of possibilities and the range of good images increase. The more gray levels you have, the better is a general rule of thumb. So here's an image with a lot of gray levels. How many gray levels? Let's look at it for a moment. Think about it. 20 gray levels, 600 gray levels, 2047 gray levels, 16,000 gray levels. The answer is I don't know, because it actually depends on what you're looking at this on and your display ability. But we could say a lot of gray levels. I would say, being a biologist, we sometimes are very loose with our math and we go, oh, that's a lot. So I'm just going to say a lot of gray levels. Thank goodness we have computers to do this counting for us, as you'll see later. But, again, here's another image with a lot of gray levels. This one has many different gray levels. You can see that everything is a type of gray. Some is darker gray, some is lighter gray, but because there's different gray levels, you get structure and you see a mountain with some grass in front of it and so forth. You see shapes that your eye interprets based on its knowledge. Again, here's another lovely image just in tones of gray. You can see the variety of images that you can make, just different shades of gray, put them in a different place on the grid that is the image, and you get all sorts of different beautiful images, including ones with, I think this is, I thought it was sunflowers, but looking at it now, it's just some form of plant in a rock. Anyway, some cool images. This one maybe has fewer gray levels, and yet it still has strong impact. This one probably has even fewer gray levels. As you can see, there's a strong contrast that is used in this image due to the putting, very black next to very light gray, and then you get something really beautiful. Okay, so one more. How many gray levels does this have? Quite a few. And one last image. A few last images. Here we go. So, gray levels. When we are talking about it in terms of photography, of microscopy, the more signal that you have, the lighter the gray level is, and the less signal you have, the darker the gray level is. And so in microscopy, we're talking about microscopes linked to some sort of digital camera, which is what pretty much any, as I like to think of it, real scope has these days. Okay, so we used to actually use film and attach a camera with film to the scope. These days, there are very beautiful, very specific cameras for microscopy. Dynamic range. It's a very important concept when you're acquiring your image to keep in mind the dynamic range. So what is it? The dynamic range, or the DR, is the difference between the dimmest and the brightest value and the number of steps in between. Basically, it's the number of gray levels that your particular image has. The camera you're using will have its own dynamic range, and the idea is to use the maximum amount of gray levels that you can based on your camera. So don't throw away gray levels. You literally paid for them, because the price of your camera depends on its dynamic range, among other things, but that's a big part of the price of it. And imaging cameras go from $5,000 up to $500,000, $500,000 ones or ones in development. But there's a lot that are $60,000 or something like that. And they have a lot of characteristics that are important to us microscopists. And one of them is their dynamic range. So the way that you speak of this in an imaging camera is you talk about the bit depth. So the number of gray levels depends on the bit depth of the camera. 4 bits is 16 levels. That doesn't really exist. It was just an old starting point. 8 bits is 256 levels. There are some very old cameras that only have 256 levels. 10 bits gives you 10 to 24 levels. This was in the 90s. It was such a jump that one of the confocals was called a 1024, as in, wow, we got 10 bits of, bit depth on this camera. These days, though, your cameras, even the $5,000 ones, are going to be a 12-bit camera or a 16-bit camera. So you're going to have either 4,096 gray levels from true black to, just white. Or you're going to have 16 bits. You're going to pay a lot more for that one. And that is 65,536 gray levels. And 0 is always, we always start with black, and then whatever the maximum value on your camera is, that's the max value. So a certain camera, let's say a 12-bit camera, which most of the cameras you encounter will be 12-bit cameras, it will start with the value 0, which is true black, and then the gray levels will keep going until 4,095 actually, which gives you a total of 4,096 different gray levels that your camera is able to acquire. So this is your camera's dynamic range. And when you're taking an image, you're going to want to use all of those gray levels. I'll show you how in a little bit. And again, the price of a camera is going to vary from $5,000 for a 12-bit camera up to, you know, the 16-bit ones are the ones that are in the tens of thousands of dollars. So what is the bit depth in the actual camera? And you might have noticed that I mentioned a CCD camera here. We'll talk about CCD cameras later on in the course, but that's a typically the cameras that you're going to encounter on microscopes have what's known as a CCD chip. It's just literally a rectangular chip that is in your camera. That is the sensor. It is what is responding to the light. And then that chip has to sort of translate that information out through something called an ADC, an analog to digital converter, or the digitizer. And it's actually the ADC that is deciding to take all these inputs and distribute them among 4,000 and some gray levels, let's say. The inputs from the pixels on the chip. The pixels on the chip are just little physical squares on a chip, basically. There's other kinds of cameras that are coming in. Consumer cameras tend to be a kind of camera known as a CMOS, C-MOS, which functions differently and is starting to make its way into microscopy too, because they're getting good enough for microscopy, so to speak. So what is happening in your camera, in your microscope, the camera that's attached to your microscope, is photons of light are hitting this camera chip that's in your CCD camera, if it's a CCD camera. CCD stands for charge coupled device, just so you know. And this camera chip has a certain number of pixels, and the photons are going to land somewhere on those on that camera chip. So it's going to land into a certain pixel, and then the ADC converter is going to read out as a gray level, as intensity. So let's look at this chart. 0, this is a chart where 0 is, again, black. And this is a camera that only has 1024 levels of gray. And so you're looking at the number of pixels that, this is a representation of the dynamic range, basically. And the dynamic range, remember, is the brightest pixel versus minus the darkest pixel. So I've written the numbers here for you. These are two different images that are represented. And one has the brightest pixel, 303 pixels, and the darkest is an intensity level of a 3. Image B has, its brightest pixel is 609, and the dimmest is 309. So which one has a greater dynamic range? Take a minute to do the math. Hopefully you've realized that they have the same exact dynamic range. They're different numbers, but in the end, 303 minus 3 is 300. 609 minus 309 is 300. So the answer is neither of them has the greatest dynamic range. These two images have the same dynamic range. And also, they're bad images. By the end of this lecture, you should know why I was able to say that just looking at this little chart. Okay, a quick note. I've hinted that I don't know what gray level it is you're looking at because it depends on your computer. I know what my computer has, and I know what the photographer the photographer can tell me. It's called metadata. The photographer maybe can tell me what the gray levels in their camera was. But by the time you're looking at it, even if the photographer was using something with, let's say, a 16-bit depth, your display is probably 8 bits, depending on how fancy a computer or phone you have. So you might be thinking your printer or your computer monitor, et cetera, usually is about 8 bits. You might be thinking when you're on a scope, oh, well, the displays are only 8 bits, so I don't have to really use the full potential of the camera I'm on. And that wouldn't be a good idea. You should always use the full dynamic range, the full possibility of your particular camera. Use all the bit depth you have, because there's info in there that is used by the software that will process your image. Even if you can't see it, even if the monitor doesn't really spit it out, and you're like, I can't see the difference between these two images, just because your monitor doesn't show them to you doesn't mean there isn't real data in those images that you're missing if you just use the lesser bit depth. So always go for the max bit depth, and then deal with it when you're image processing. And you'll note sometimes you can have an image and it looks great on one computer in one software, and you throw it onto a different computer and different software, it suddenly disappears. That's usually a bit depth issue. So if that happens, let's talk about it in class. I'll show you how to fix it. So here we come to the histogram. Actually, I'm going to back up a second. I feel like I just told you, oh, we'll talk about it in class and we'll fix it. The answer how to fix that is to go to your histogram and fix it there. So this is referring to what I just said on the previous slide. So the histogram is a microscopist's best friend. You must always have a histogram of your image. Anytime you take an image, before you take it, know what the histogram is. When you're looking at it to process it, know what the histogram is. Just always find it. There's a lot of different software, and every single piece of software out there for digital images has the ability to show you the histogram. Sometimes you have to hunt, sometimes it's front and center. Histogram is the key to knowing whether an image is good or not. So what is a histogram? A histogram itself is just a general mathematical term for a graph that shows you a count, like you've counted something, discrete values meaning actual things that are different from each other. So this is a histogram of what might be in my fridge on a certain day. I went to my fridge and I went, how many apples do I have? How many oranges and how many tomatoes? And it's always the x-axis is always the items. Okay, so the fruit in this case, well, fruit, tomatoes are fruit too. And then on the y-axis, the vertical axis, right, is how many of that particular item do you have? So you can look at this histogram and know that I have 10 apples and 20 oranges, and I think that's 15 tomatoes, and you can, know the total number of these items I have in my fridge. But more interesting than a total number is the breakdown by what kind of fruit / vegetable. Tomatoes are kind of in that in-between category, right? Biologically a fruit, nutritionally a vegetable. Okay, so a histogram is just a display of things that you have counted. So in microscopy, what are the things that we are counting in our histogram? We are counting gray levels. Ta-da! Okay, so to do that, I'm going to actually pause and go back to my iPad as soon as my mouse will come back to life. I'll let you look at this pretty histogram here for a second. Okay, so here is that digital image from before. This is basically showing you a very small chip. The actual chips that you find in a CCD camera have thousands of pixels. This is 1 pixel on the chip. So this pretend chip just has 1, 2, 3, 4 times 3, 12. So 1, 2, 3, 4, let me do that on here, times 1, 2, 3. So there's 12 pixels. That's like total number of fruit in my fridge, whatever. It's interesting, but not very useful. What we want to know in this image is how many pixels are light and how many pixels are dark. And so we would make a little histogram here to the side and go, the value is 0. And then the top value in this pretend camera is, let's say, I was going to say 300, but actually, let's just call it 1023, like a real camera might be. And how many pixels do I have that are 0? Well, I have 1. We'll put 1 right here. And so I will make a little line going, I have 1 that is 0. And then how many pixels do I have that are value 2? I have none. So that goes down here. Value 1, 2. I have another one that is 3 here. This is not going to be totally to scale, but how many? Oh, just 1 that is a value 3. So I'm going to make a little column here for that pixel. I'm going to check them off as I count them. You're going to actually get to do something similar. I have, what else? I have a pixel that is 12 and one that is 13. I'm going to bin them. This is called, I'm going to call them the same thing. Well, okay, I won't. Let's do. So I'm going to have 1 that's 12 and 1 that's 13. Then I'm going to have 1 that is 26 and so on. Anyway, what this is going to be, this histogram is not going to be very interesting because it's going to be one of each. But actually, no, let me keep going. You notice there's some in the 20s, and then there's a huge gap. There's none that are 100. So there's going to be nothing for a while, and then we're going to come back up with some values. And a histogram is actually a series of little lines, but the way it's going to get displayed for you is the graph that connects the dots. That's the tops. So this histogram will be something like this. It will look something like that. Okay, not quite. Let's do a different one with a better, actually, yeah, let me just show you some images. I'm going to draw them for you. And I'm going to draw them as you might see them. So like here, for instance, let's say there's a cell. And because this is a fluorescence image, the background is going to be really dark, because that's what we want. We want the fluorescent, in a fluorescence image, we love a true black. And then because I'm obsessed with fluorescence, and this is really a program about fluorescence, I'm going to draw you another fluorescence image. And this also has a dark background, but wait, I bet the histogram's going to look different, right? And we're making the nucleus kind of dark. So let's draw the histogram of this guy. What we're going to see is a lot of pixels. If we, turn this into a grid, a lot of the pixels are probably going to start with a black value. And then there's not a lot of mid-tone grays. And then we're going to start getting signal up again near the lighter areas. And because this is a good image, I'm going to have it come down like that. Okay, in this image, there's going to be less, count-wise, there's going to be actually less dark pixels, and there's going to be still a lot of, very light ones and not so many maybe midtones. You might be looking at this going, the total's not they should be the same total. And that's just because I didn't draw them that great. But what I'm trying to get at is in fluorescence, you'll see two peaks, usually a dark peak and a bright peak. That doesn't really matter. The shape of your curve doesn't matter much, actually. If you had, well, like that image I was trying to draw, you might have an image that looks like this. That's probably a bright field image. So fluorescence, bright field, it could be all sorts of things. The actual shape of this curve isn't important. It's not why you look at the histogram. The reason you look at the histogram is when you're trying to figure out how much light to give your specimen or how long to expose it, you don't want a histogram that is just like this, for instance. This is your full dynamic range, 0 to the top. So here, these are okay histograms. These are decent histograms as I've drawn it. So decent images. This is how I can just look at a histogram and know it's a bad histogram. This down here, this is a bad histogram. This one is not using the full dynamic range. I would much rather, here, let's pick a color. Let's make it, whoops, sorry. Let's go back to this. Okay. Let's pick a nice green. So if I am looking at, okay. Let's make that go away. I'm looking at this particular bad image. I'm going to want to try to get it to look like this, probably by changing the exposure. Now it's a good image because I'm using the full dynamic range. Let me show you a different way of doing bad. So one way of doing bad is that you do not use the full dynamic range and you're throwing away gray levels that you paid good money for on your camera when you bought it. The other way of doing bad is often comes from overexposure typically, and you're kind of blowing out your camera. And what you will see is that your curve, well, not your curve can have ups and downs in the middle, but the ends of your curve do not dip down. You'll notice that all of these other images, here, let's get the green for good tool. This one dips down and doesn't really go use the last few numbers or the last few gray levels. It's also kind of good if you don't really start at black, but close to black. In fluorescence, we push in. Sometimes we saturate the black areas, and that's sort of questionable. I mean, it's okay, it's not great, but really you want to leave some room on your gray level. You don't want to use all of the gray levels. You want to use most of them, but not all of them. So because when you look at this little guy over here, you don't know, you're counting pixels that are super black and very black and extremely black, and you're lumping them all together, and you're losing information there. In class, I will show it to you in some images because we will look for saturation in images. This is called saturation. What usually happens is saturation over here, where the image looks blown out. It's just so bright that you can't see any details. To see things, you need contrast, remember. And what's happening is you're basically losing contrast here. I know green is for good, but this is actually a bad thing. when you are throwing away your ability to have contrast by just making it so bright that everything ends up being the brightest value, and you want to be able to tell the difference between, you know, the brightest value and the next brightest and the, you know, a little less bright than that and so on. And to do that, don't go all the way to the edge. Don't ever have a brightest, don't use the brightest value possible on your camera. Have your actual brightest value be like here, just sort of kind of end. This is good too. This ending is really good. So again, there's a ton of info on a histogram. Just looking at the histogram is so important. Always look at it as you're acquiring an image, look at it afterwards, look at it as you're processing the image. Okay, so we're back to the PowerPoint where you've got the words around what I just said. So a histogram is a representation of the dynamic range of your system and also where your image falls on that dynamic range. So this is a great image. Looking at this, I'm using the full dynamic range and I'm not too close to either end. I'm leaving a little room there so that I know that I'm not just blowing out the ends and I'm not losing any info. Here's some examples of, well, the top one is a bad histogram. So I don't need to look at the actual representation of this image, the thing we would think of as an image. I can just look at the histogram and go, oh, that's not good. That's not going to be a good image. There's not a lot of contrast in it. It's all going to look mid-tone gray, and you really were throwing away a lot of the ability of your system, of your camera, to get a better image. Now, sometimes you take an image like that because you don't have much choice. It's a living specimen, you're going quick, it's fine. But just know that it could have been better, okay? That's the important thing. And if you can, and when you can, try to go for a histogram that looks like the second one, not the shape of it. So not the fact that it goes up, comes down, goes up, comes down, whatever. That's not important. What we're looking for is the ends of the histogram being almost near the end of your values, being at the extremes of your x-axis, but not quite to the very end. Close, but not exactly there. Then that's a good histogram and a good image. So saturation, I tell you about this up front and soon and early because it is something that a lot of microscopists do. And there's all sorts of published images where I'm just always shaking my head going, what? How did you publish that? Why? Etc. It's a thing that sort of the inner circle of actual microscopists, we're all in agreement with. We're trying to get journals to not publish saturated images, etc. So I'm trying to indoctrinate you early and often to almost never saturate anything in microscopy, anything in science. Has an asterisk to it, as I like to say. Like sometimes you just got to do it for whatever reasons, but generally speaking, don't saturate. So saturation, like I've said, can occur at either end of the dynamic range. And once you're in that zone, you're lumping together a lot of gray levels into the max level or into the zero level, and you're just losing data. And you can see it on the histogram, but you can often see it on the image because if it's a biological image and there's just a bright, evenly white splotch of your image, that's saturated because biological images all have slight variations from pixel to pixel. So if you're not seeing that, you're probably looking at somebody who just overexposed their image. And you're going to play with that in lab this week. So you'll get a chance to play around with this and get a sense of how an image can just be saturated in either direction. But honestly, usually it's a question of too much light and too much brightness. So like I said, there's no nothing in biology or science is 100% in biology anyway. There's always this asterisk, like, except when. So never saturate your images ever, except when. Except when you know for sure there's no image in there's no info in the dark pixels, and you decide, okay, I'm gonna just make it a perfect black background, because fluorescence images, we love having that black background. It's better to leave the background more like a dark gray and then deal with it later, just in case it turns out maybe there was something useful to know in that background. But you know, there's some of your own judgment that comes into this. And sometimes a piece of your fiber from your lab coat or t-shirt, if it's a cotton fiber or any sort, a lot of fibers actually, um, if it's cotton or certain materials, it fluoresces brightly. And so you suddenly get this fiber that landed in your specimen, and there's this hugely super bright little fluorescent tiny thing. Um, and you can look at it and go, I've seen a million of these. I'm going to choose to ignore it. You do not get to cut it out of your image. You do not get to make it disappear via Photoshop. That's the science ethics behind it. You can choose not to take a picture of it. So if the good stuff is far away enough from it, you just ignore it. But sometimes it lands right on the things you're trying to look at, in which case you're stuck with it, in which case it's okay to saturate what is called schmutz, SCHMUTZ officially. It's a Yiddish word for junk, dirt, etc., that a lot of microscopists use. So if there's schmutz in your image, basically something fell in there and you're pretty sure it's not part of the specimen you're looking at, and it's super bright, you can choose to ignore it and, you know, blow it out, saturate it out. Okay, so again, here at the top is a great image. I'm looking at the dynamic range. It's large. I'm looking at the ends. They go almost to the end, but not quite. And as long as that image is also focused, it's probably an just wonderful microscopy image. The one on the bottom, even if it's focused, it's saturated at both ends. It's terrible. I can't tell what's going on. It might be artistically beautiful, by the way. That's fine. You can choose to do it for artistic reasons. But in terms of science reasons and the info in that image, it's not good. I wouldn't trust you if you showed me this. If I'm reviewing your paper, I would bounce it back to you and say, take a better image. I don't know what's going on in your image because you've saturated at both ends. All right, on to the next great topic in digital images. There's two concepts really that you need to understand for to understand what a digital image is. One is the lookup table. Well, okay, three concepts. One is the fact that digital images are a bunch of gray levels. Two, the histogram. And three, the lookup table. You will become such a fan of lookup tables, hopefully, after this class or even after just this week. So what is a lookup table? Well, let's step back for a second. We know that a digital image is a grid of numbers, right? And now you know those numbers refer to the gray level, the intensity, on a scale of 0 to whatever your top value is. We can always count on 0, 0 being black. There's always going to be a black or light, you know, dark gray, a 2, a 3, a 10, something like that, still dark gray. And then to whatever your highest value is of, you know, a lot of light, let's say 4096, for instance. So those are the possible gray levels you have. And each pixel gets assigned a number. Is it 32? Is it 49? Is it 303? Whatever the gray level it is assigned to a pixel, and that's in a grid, and there's your image. In the case of microscopy cameras, it's always a rectangle because it's actually the same. I think it's a Sony chip. It's the same chip in every camera, regardless of the brand. The CCD chip is made by I think one manufacturer. Anyway, so your digital image comes from the microscope, which is producing photons, right? You're shining light through your specimen or bouncing it off your specimen if it's transmitted or reflected. Either way, there's photons that are being collected by your objective, and they're going to end up through, they're going to run through your microscope, be directed by mirrors, etc. They're going to end up hitting either your eyeball and or your digital camera. And that camera has this chip, as I said. The chip, what happens on the chip is there's a voltage flux. So electrons are now involved, basically. And things get counted and assigned to gray levels. And the same image will get assigned to 0 to 255 gray levels if you have a really ancient cheap camera, or 0 to 4096 gray levels, 95, whatever, to about 4000 gray levels if you have a better camera. So there's, notice that there's a process of what is called binning, like picking, you know, turning analog, a bunch of waves and photons into something that we can count. So it's not quite exactly like the fruit in my fridge, although it's a little bit like the tomatoes. Like, do we count that as one fruit or two fruits? It's kind of more like that with photons. But basically, a bunch of photons is hitting this chip. And then your camera is turning that into surges of voltage fluxes. So now we're talking electrons, and we're assigning gray levels to each pixel. To each part of the chip, we're assigning a number. That is your output. That is what your computer sees. Like, the file for your image is just a series of numbers with location. That's all it is. It's numbers. Now, something has to decode these numbers and display them to you. Okay, so you record it, you save your image as a file. Now you're going to open it up on your phone because you emailed it to yourself or to a different thing. However you're going to do it, when you open it up in whatever display software you're using, there is something called a lookup table that is decoding that information, that series of numbers, and it's turning it into an image for you. So for this, let's go back to that original, let's see if it will let me out so I can go back to that original draw. Okay, here we are at that original image that I first showed you. Not sure what it's an image of. Well, let's find out, because our brain isn't able to look at this series of numbers placed in a certain location and decode it. So let me actually color it in just like a lookup table would do. And by the way, this is going to be your assignment next week, so come back to this. So I know that the smaller the number, the darker it is. So I'm going to start with, oops, I'm on eraser. Let me get out of eraser, go back to black. Yeah, okay. So interesting. It's giving me shading, but I want to just draw it. So I know that this pixel here is as dark as it gets. I'm gonna draw it for you super dark, as much as I have time and you have patience for. So we're gonna just quickly make it nice and black. This is exactly what I'm gonna ask you to do next week, so you can learn. Some of you have had a lot of art classes, which I haven't, and probably can do this in a more beautiful, quicker format. That's great. If you can't, don't let it stop you. You can still have a career in science. Okay, so that's super black. And then 3, I'm gonna make it, I'm not gonna sit here and make you watch me entirely. So I'm gonna arbitrarily actually choose to make a different, like make them visually different. It's still nice and dark, but Not quite as dark. This is where you notice I'm making this choice, and the lookup table does that too, by the way. I could have made 3 just the same as 0. And then let's see, these high values, we're gonna leave them, we're gonna take out the value. And how do we make this? And then this one is, 12 and 13, they still got some color in them. Some nice and black, but they're not quite as dark. 23 is next up. It's still got some shading. Maybe not as much. 37, some. 42 also, but not as much. This one barely has any color. Also barely any color. Hardly any color at all. Here, let's give it a little bit on these. Great. And that one is the lightest of them all. Just gonna make them look a little bit different so you can see them. So what image do we have here? Nothing really much that I can still decode, but I certainly have a pattern, and I can see, let's see, if I had to sort of smooth it out, I would say that there's something that's sort of this shape in here. Of course, I'm making it, distorting the shape. This is called distorting the aspect ratio, what's tall and what's short. But this is the general idea. I have something that's this shape out of this weird image. You'll get an image that is more interesting next week to decode. But that's it. I just acted like a lookup table. I just turned those numbers into intensity. Well, those numbers are intensity levels, so I just came up with a way to display them to you. Okay, so again, what is a lookup table? It is a set of instructions that your digital device uses to display your digital image. So it determines how your original values are displayed or saved. And it's actually just a table, as I will show you in a moment, that says if the original value was 0, display it as 0. Original value is 303, we'll display it as grade level 303. And you might say, actually, let's come back to here. You might say, why would you ever do anything other than display it as the original value? I'll leave that question hanging as we go through this. So remember, the histogram counts the values. It says, how many pixels do you have at each value? It can actually show up as a table also, which in some software you can actually call it the table. Usually it's giving you the chart of that table, which is what we've been looking at. Here's something to be aware of when you're dealing with different software. Are you looking at the histogram of your original data or the data as transformed by your lookup table? Depends on the software. Sometimes they show you both, sometimes they don't. So let's look at this image. Here's, again, another image. And it's a little simpler than the first one I showed you. Here is a table where we count how many pixels there are of value 0, and you can double check me on your own and go back and count. But basically, there are 1, 2, 3, 4, 5, 6 pixels that have value 0. There's 2 that have the gray value 1, 3 that have 2, etc. Here's the table. And then we're going to draw this out. So there's that table where we counted that image. And let's chart this table. And this table, this chart of the so it's a table on the left and it's a chart on the right. And this chart is called the histogram. Yes, good. And it's blocky like this, but the software will always just display it for you, almost always, as line of the tops. So it's just a quicker way to look at the histogram. Okay, you might notice that we didn't saturate the bright end. We're a little too far over and near zero, but it's an okay-ish image. If it's fluorescence, it's probably just fine. Okay, so that is the actual image itself that you're looking at. And there's the histogram that you just created. And then there's me coloring in that image using a lookup table. So let's show the lookup table. Here is the lookup table. The red line is the lookup table. And by the way, this is how you will see your image presented on most software. And if it doesn't do that, throw away the software, use something else. Seriously. Like, so there's the lookup table is one line. So it's on the same chart, basically. And then your actual data is the other line. And it's really easy to tell which is which, because the lookup table is a line and your data isn't, it's all squiggly. So the lookup table that I've drawn there is the one you would think we would always use. And it's your standard starting lookup table. It's called linear. Even though all lookup tables are a series of lines, this is the one we call the linear one. So it's the one that intuitively makes most sense. The original value is 0. Let's display it as 0. The original value is 1. Let's show it off as 1. Original value 2. Oh, let's call it a 2. 3, let's display it as a 3. 4, display it as a 4. And 5 as a 5. Okay, so when you chart 1 versus 1, I mean 0 versus 0, 1 versus 1, 2 versus 2, you get that nice 45-degree line that we have here, the red lookup table. So in other words, show me my data exactly as it was. Give me the exact original image with the exact same gray levels that I started with in the image. And of course, yes, a lot of the time this is what we want. We certainly want access to this image. But there are reasons why we sometimes mess with the lookup table and don't use just a straight up linear lookup table. So let's see what happens if we mess with it a little bit. Let's play with the lookup table. And by the way, this is totally addictive. In an ImageJ, or Fiji actually, newer version, basically, the software that you're going to be using, there's some programmers or somebody who put in a zillion different lookup tables randomly, no info in them, but they're super fun to play with. Again, art, which is total utter freedom, is not as, well, it's not reality based in the same way, right? Okay, so let's come back to this. Let's decide that any value that is less than or equal to 2, I'm just going to draw it the same way. I'm just going to call it true, real black, authentically black. Like, so if it's 0, if it's 1, or if it's 2, I'm going to color it with the same gray level. I'm just going to decide now that they're all lumped together. So 0 is 0, 1 is not 1, 1 is 0, 2 is 0. And then you're going to get this line that is not a 45-degree straight line anymore, but it has different slopes. And this is your new lookup table. And think about what the image is going to look like. This is really useful, actually. It's a legit thing to do, by the way. It's really useful if you do what I said and you took your original image, it's fluorescence, but the background is kind of a little bit more dark gray than black. But now you've double checked, there's nothing interesting in the background, and you're like, you know what? Everybody's going to want to see fluorescence background is really black, or because it's just the culture standard. So I'm going to now turn the dark gray background into total solid, beautiful black. This is the lookup table you'll use. And like I said, it's legit. It's up to you to a certain extent to decide if there's data there or not and to know about it. you might be wondering, do people have to report this? And the answer is no. And hopefully you're thinking, what? Because that's how I feel, and all the true microscopists. We're trying to get standards on reporting. um, all There's so much manipulation that can happen to an image, right? The bottom line is don't trust images. I think we know that by now. But so in science, when it's reported, when it's a paper, how do I know that I can trust this image, that the person did a legit manipulation on the lookup table like I'm showing you, versus there's a bunch of things you can do that aren't so legit. It would be nice if folks reported it. So that's what we're pushing for, basically. And some journals are there, some aren't. And Bioimaging North America, this new network that I'm a part of, therefore you're a part of, is actually working on imaging standards in reporting and doing it. Okay, so just, word of caution, what can you do with your original image? Anything. What can you do and still have it be legit science? Just a few things. Less is better. If you're not sure, that means you probably can't do it. Always save your original image and then go, make a copy and mess around in the copy, because sometimes these things are permanent. So always, you're going to end up having copies and copies and copies and copies of each of your images, and that's fine. So this is what happened when I made the lookup table more favorable to, I just sort of pulled it down and made more values true black. I made the background more black, which is again what we want in a fluorescence image. There's more contrast. There's the original image, and these are, it's not the great, but anyway, you see there's it looks different, right? And the sort of cross pops out a little bit more now that you didn't see before, etc. So there's a lot of just knowing the context of your image, whether for you to decide if this is a good idea or a bad idea, which image is better. It just depends on what you're trying to show and how and what was the dynamic range of the original image. So that's just one tiny example, but there's a lot of lookup tables that do a lot of things. Color, it's back. I asked you to set aside color. I broke my heart because I love color, but here it is. Color is back. And this is how you get color, is you just apply a color lookup table to your image. And most cameras in microscopy are black and white because they're more sensitive, which is another thing we want in camera. We want it to be able to pick up any tiny little bit of light that there is. And to do that, you need a black and white camera. And then you just remember, was that a green image? Was that green? Was that red? You write it in your notes, you throw a lookup table on it. There you go. Color is back. Okay, there's actually on your computer, on your software, when you're imaging, there's an overlay that will be shown to you that warns you if you're saturating something, and it uses a particular lookup table that just gives you color. It's color coded when you're saturating, and so it's very useful, and pretty much all software has this. It will often look like a little French flag because those are the colors they use. So it just colors your overexposed and underexposed pixels so your eye can go right to them, and you can make a choice and say, oh yeah, I'm going to leave it like that because it's just a fiber from my lab coat, or no, oh my God, that's exactly what I was trying to see and I'm saturating it. Oh my gosh, let me back off on the exposure. Okay. And like I said, sometimes we just do crazy lookup tables because we're in a mood. This is for no particular reason. I'm just going to make the ones blue and the threes red, whatever. So you're always using a lookup table, whether you know it or not. There's a lookup table behind every single digital image you've ever looked at and ever will look at. If you're displaying a digital image, there's a lookup table. And you can color a black and white image. You can change the black levels like we did. This is called changing the offset. You can change the contrast, which is doing a contrast stretch. That is a wonderful way to manipulate the lookup table, and we're going to talk about it next week. you can invert, you can make black white and white black. And sometimes that just allows you to see your data in a new way. You can actually just change the brightness, make everything brighter, right? Or dimmer. And as I've said, you can look for the saturated pixels and basically have this little warning flag over your image. These are just some of the uses of the lookup table. So when you're imaging, you want to think about your original image acquisition, right? You're looking at the histotag, I mean the histogram. I say histotag too much these days. Okay, so you're looking at the histogram. And are you physically changing something when you're acquiring your image? Are you giving a longer exposure, et cetera? Or are you in some of the software? I'm just sort of warning you, sometimes it will display the image different for you because you've changed the lookup table, but it won't save that. So you'll take a bright image and then you'll open it somewhere else and you'll be like, it's so dark. And it's either because the new software is interpreting that image differently as a different lookup table, or your own software was giving you a little mask, if you will, but it didn't save it in the image itself. So yes, it gets complicated to take digital images, and it's okay to take a million. It's always a better, like if you're not quite sure what the software is telling you, then, you know, overdo it. Always take more images rather than less images. And you might be thinking, how is software not going to tell me? And you'll see the software in microscopy right now is terrible, has been for about 20 years. That's another story I'll tell you in the next session on this. But don't trust computers, basically. Know what they're doing. Don't trust software. Try to understand what it's doing and whether you want it to do that. Know that it's very interesting. You can know that different software sometimes just puts different lookup tables intrinsically into your image because it kind of knows what it thinks you're looking for, and it'll just make it pretty that way. And I think we're more aware of this now that our phones are explicitly doing this to our images, but it's been true always of images that there's always a choice. And how do you display this image? Do you accent certain things? Do you make other things appear, you know, more obvious, less obvious, etc.? So just kind of always pay attention to that. And so the things that affect a digital image and the data they have and what they look like include, of course, the detector, the camera. Is it a CCD camera? There's fancier ones called EMCCD, or PMT is something used in confocal. We'll come back to, I mean, we'll talk about that later on. The dynamic range of the camera, I talked really briefly about the sensitivity, just how good it is at picking up your signal. What is the ADC converter up to? Who's told it to do what, how, and how to treat your data. And also the size of the pixel, which has to do with the sensitivity too. Although, like I said, in microscopy, most of our pixel sizes are most of our chips are kind of the same from camera to camera. The software, however, is very variable. And the software, something else to be aware of is the image format. I'm going to talk about that more next week. You know that there's different kinds of formats that the image is written in. Of course, the lookup table, as I've been saying. And also, does it save your metadata? Assume it doesn't. Metadata being, is it a 10x objective? How long was the exposure? Things like that. Assume that it doesn't, and you're going to write it down again in the next lecture. We're going to get into that. And also, of course, your image might be gorgeous to your eyes on the microscope. It might be gorgeous even when you first open it up, but then you have to show it through a really bad monitor, printer, or LCD projector. Just know that that happens a lot. LCD projectors in particular are terrible to your microscopy images. So sometimes we make high contrast, super bright versions just because we know we're going to use them in a talk and it's going to go through a projector. In Zoom days, not so much of an issue anymore. Okay, so to acquire a digital image, you've got to use the histogram, have it open, have it looking at it, make sure you're seeing it. Do not saturate the ends, go for the max dynamic range that you can get. You're going to learn to work quickly because presumably you're working with live stuff and you just want to be quick as an imager. You want to be able to put something on and just go snap, snap, snap and get some really good images. But at the same time, and this is going to slow you down, you do have to write down what you're doing in your notebook. And again, we're going to go over that soon. And once you know what a contrast stretch is, which is next week, then you can perform that if necessary. So that's it for this section.